Okay, I'm back. I've got my reading glasses on now. And let's see. We've got our inertial turn heading function sketched out right here. We like to go 90 degrees, but we don't actually have code in that function that I created over here in this file. It's a big fat blank. So if I ran this code, my robot would do nothing. So let's now get up my handy dandy whiteboard and talk about how we're going to do this algorithm. I hope we can see some of this. This is my, pretend we've got my robot with my inertial sensor facing in this direction. And it's calibrated, so now 0 degrees heading is that way, and I want to go to 90, which is over that way. I want it to turn that way. And as it's turning, here's my current or actual heading. My target's over here. So I'm going to start my wheels spinning, but as they're spinning, I'm getting closer and closer. In other words, the error between my target heading and my actual heading is getting smaller and smaller. So my actual heading is the current reading on the inertial sensor. And since mine's on port 13, I can actually plop into a variable if I wanted to, the current heading when it's turning through a loop. The command is inertial 13.heading, and you put the parentheses. And the target, again, is what I fed in to my rough sketch of a function. So I need to be able to calculate in this function what my error is. I want to constantly figure out what my error is. I want to be constantly measuring where I am, what the heading is of my inertial sensor, and see if how close it is to 90. So I'm going to get this error. And as the error gets smaller, I want my speed to go down. And I'm going to use what's called proportional control. I need to be able to change this error that I'm calculating into some type of meaningful motor power, because this is where I'm getting my power from. Because as you noticed, and I did my function here, all I'm feeding is target heading. There's no motor speed. This motor speed is coming from this little magic right here, magic math. I'm going to use that error that I calculated. I'm going to find a constant that makes that error into a meaningful motor speed. This is called tuning a proportional control. If you're in robots long enough, you'll also hear of PID control. That stands for proportional, integral, and derivative control. We could add those other two terms to this algorithm later for those that want to. But this will get you a very good first approximation, awesome turn. And it's how I did the turn, or the autonomous, that 20-point autonomous in 13 seconds. I simply used proportional control, and I got a very good performance. So the key takeaway is you need to calculate the error as you cycle through a loop, and then always take that error, multiply it by a constant that I usually start with 0.5, and that's going to give us the motor speed we're going to put in for running our motors. All right, so just to give you an idea, I don't know if this is any helpful or not, but again, if we did an instantaneous reading on heading, say initially at 0, and then we sampled every 15 degrees, it's pretty obviously it goes down, but the error eventually approaches 0. And we're going to be constantly taking that error, say like at 90. If I use a KP of 0.5, I'm going to be at 45% power. But if I'm going to be doing a target heading of, say, 270, 0.5 would, that would be 135, which is more than 100% power. So we're going to tune this constant that we're going to use, and I'll show you the process for that once I have my demo robot back at home. I left it at school, so I can't show you a lot of these things, an actual working robot. All right, let's go and get rid of my fancy whiteboard, and let's start coding. We know that we need to have some variables. We need to have an error. We got our target heading. We need to know our error. And let's start with, let's do our error. That's not the most important thing, but it's key to this whole thing. So I'm gonna make a double. And I'm going to call it error. Sometimes people call it current error because basically what you're doing, you're updating it all the time. Actually, no, let me do that. I'm going to call it current error. Current error equals, okay, and we're going to do our target heading minus our actual heading. And we can get that simply by calling the inertial sensor. And mine's on port 13, and then calling the heading, and it'll give you that value. All right? And I put a semicolon at the end of this command. And of course, it doesn't like something, and I can tell you, you can hover over it, it's not being used. Don't worry. We're going to use this supposedly unused variable shortly. All right, so we created a variable, and we actually initialized it by doing a math function right here, taking the difference between the target heading and our actual heading. Next, we need to do our we need to do that KP, that constant. And I'm going to initialize it. Like I said, I like to start off with 0.5 and then play around with that value and see what happens. Again, it doesn't like it because it's not being used. It will be used. Do I have all of my... Do I have them all? I think I have them all. If I forgot something, I can come back and do it. All right, figure out what it is. So, I want to keep reading my inertial heading as I'm going through a loop during this turn. So, but what's going to control this loop? What's the condition? I mean, I'd like my error, my current error, to be 0. But good luck getting your fast-moving robot and this high sampling speed on your controller to pick up 0 exactly. You can try it. And what I do is I typically look for a small amount of error. I usually say, hey, if my current error is less than 4, I'm good to go. And that's a very good way to do it. It's worked well for me. So what I'm going to do is I'm going to make a while loop. While my current error is less than 4, I'm going to do something. I've already got my current error calculator right there. I need to turn that into a meaningful motor speed. And I just remembered I forgot to make my variable called motor speed. Let's do that. Double. Call motor speed. Well, if I can type correctly. Where's my shift speed? And I'm not going to initialize that one. That's going to come in down here because I'm going to do that right here. While my current error is less than 4, I'm going to do motor speed equals my KP times my current error. Great. I got motor speed now. Now let's make our motor spin with that. I forgot, what do I have for my motors here? Do I have motors configured? Dang it, I don't. I gotta do that. All right. You probably already have yours configured, which is great. Let me just do that. Let me just pause this. No, I'll just do it. You can just speed through this, hit fast forward or something. All right, let me get my motors in here. I'm just gonna do 2 motor, all right, right. And we'll put that on port, I don't care. I'll put it on port 1. And the ratio will be the default 18:1, and I'll do a false for, no, I'm going to do a true for the right, the reverse, oh my gosh, true, oh my gosh, really speed through this one. For reversing the voltage on the right side, and then left drive, I'll put that on port 2. And the ratio will be 18:1, and I'll do a false on this one, and I can't even spell false correctly. False. Okay. And let me go put those up here in my robot configure. header file, extern, motor, right, extern, motor, left. And you guys will mostly have 4 or more motors on yours. I'm going to hit build because when I make that many changes, I like to see that I've got the configuration correct. Yay, yay, yay. Okay, let's go back to my turn to heading because now I can start using some motors. All right. I'm going to do the left. Why not? Leave the left first. Left dot spin. And we're going to do forward. And we're going to say motor speed. And I'm going to do PCT. And I'll do the right one. Come on. Why isn't it like this? Dot spin. Motor speed. PCT. And if I'm doing a turn, I need one motor going backwards, and I'm going to do a clockwise turn. So my right motors need to be going in the opposite direction. And is this not linking because, let me just go ahead and build this and see what it has to do with a linking issue. Oh, it's ambiguous. Yes, they didn't like right, left. I have to give it a better name, don't I? Dang it. Well, that's easy to do. All right. Right motor. I'll just call it right drive. Right drive. Left drive. Go back over to here. Right drive. Left drive. You get to see live coding, mistakes and all. This is real life. Now I need to go back to my function and change that up. Drive. All right, and let's hit build. There we go. Everybody's happy. I think we're all happy now. All right. Robot configure, rep drive, robot configure, right and left drive, turn to heading, and it's still using an undeclared left drive? No, I'm not. Did I forget something? Extern, motor, left drive, right drive. Well, I hope that's going to clear because, dang, somebody else seeing the problem? I'm not. I got it spelled right. Left drive, right drive. I wonder if I start typing it in again differently. Let me just do this. Oh, gosh. This system can be so slow at updating. Anyways, I'm all happy. Hope you guys just whiz right through that on fast forward. So now we have our while loop, current error is less than 4. I have a problem here. I already know. Our error can sometimes be negative. And so a negative is less than 4, and so it wouldn't enter into this. So take, for example, what if I'm at a current heading of 90 and my target is 0? That's negative 90. Let me go ahead and correct that right now. And I'm going to put in absolute, I want to take the absolute value of that. And to do an absolute value of a double, you have to do floating point absolute value, which is a FABS. All right. So FABS, it stands for floating point absolute value. So it'll just get rid of the negative sign and it'll compare that current error to actually 4. And so if I have a negative error, it'll go through the loop if it's greater than 4. So first thing I want to do is get my motor speed. I'm going to take that current error, which was initially calculated up here, apply the constant value, and then take those motor speeds and get my motor spinning. As my motors spin, I got motion on our robot, and guess what? I'm no longer at my initial heading. I'm at some new heading, and I want to update my current error. My error has changed, so I'm going to update current error with my doing the target heading. If I can spell target correctly, target heading minus inertial 13 dot heading. So basically, I'm updating. I did an initial read. My robot was stopped. My robot's now moving. I need to update this error. It's going to come back up to the loop, and it's going to go, is the current error less than 4? If it's not, the error is now going to be smaller, hopefully. It should be. It's now going to then update the motor speed. And now the motors are going to slow down. What you'll see is you learn to tune these things. You can actually tune this, and you'll see it can actually go so fast that it overshoots. It'll stop, but you'll have less accuracy the higher this number gets. Anyways, we've updated this value. That's the important thing. Whenever you're doing a loop and you're using a sensor, update the sensor value. And in this case, we're updating current error, which is based off of the inertial sensor. Okay, what's the case if the current error is less than 4? We're very close to our target. Well, we want to stop our motors. So outside the while, we want to jump outside the while loop, and now we want to stop our motors. Left drive, dot stop. And I recommend putting a brake on this one. You get a cleaner stop this way. Right, well, that was odd. Right drive, dot stop. Okay, this is an initial attempt. I'd like you to try running this code and see what happens. There are some things you need to do to fine tune this, but this is an initial first step. I'm going to hit build and see what happens, and we'll all be happy, right? Do the happy dance because it's not building, is it? Daggone it. What did I do this time? Oh no, build complete. Okay. We're all good. We're all happy. Yay. Okay. That should get you all started. The other things you need to do is just play around with this value right here, and you might find something interesting in the directions of your turn. Because there's two ways to do a turn when you're going to a heading. It can either be a clockwise or counterclockwise turn. And you also want to always take the shortest path. There's the short path, there's the longer path around. So play with it and see what happens.